WarsawJS.
Hello mates, my name is Tadeusz. I hope you're awake and are at least alive. Last time, in July, we were talking about resizing holiday images the content our way, using the seam carving technique. Today we'll continue our advantage with holiday images. We take plenty of them and send them to our beloved, or like Bond, James Bond, to the leaders of our organization. These images can be cute, funny, amazing, educational and inspiring. But this is only the surface of the reality, only the front end. And the true meaning of these images can be hidden deep inside them. For example, can you distinguish these two images? I'm pretty sure you cannot. I can assure you that one of these two pictures is just an ordinary photo, and the other one contains a deeply hidden message. I promise you I'll reveal that message to you at the end of this lightning talk. By the way, does anybody know what building is this? And where is it located? It's so-called Warsaw of the North, the Braniński Palace in the Białystok, Podlaskie Voivodeship in Poland, of course. Today I will introduce you to the idea of steganography, a technique of hiding messages in multimedia files on the example of pictures. Unfortunately, before we get serious, I have to warn you. We are now leaving the safe, colorful and charming land of front-end and we plunge into the deep bowels of computers, into a dark and misty land of single bits, processor registers and magic operations as bit masking, bit testing and setting and resetting them. Lasciate ogni speranza voi centrate. Also be warned. You may know, I presume, that every image can be represented as a two-dimensional matrix of pixels. And some of you may even know that each pixel may be represented as some number of bytes. How many? It depends on so-called color depth. From 8 pixels per 1 byte to 4 bytes per 1 pixel for full color images with so-called alpha channel. It's some kind of info about the pixel's transparency. We can treat these bytes as 32-bit integer or as separate bytes and process them independently. With steganography, we dive even deeper and will operate on single bits of these color plane bytes. To fully understand the whole process, let's recall the basics of the Boolean logic at the bit level. You may remember that there are 3 basic bit level operations. First, the logical sum, known as the OR operation, with plus or a vertical line as the operators. And here we get 1 when at least one of the operands is 1, and 0 only when both of them are zeros. Second, the logical multiplication, known also as AND, with the asterisk or ampersand as operators, and here we get 1 only when both of the operands are 1s, and 0 when at least one of them is 0. And the last one, the logical negation, the NOT operation, with the exclamation mark or tilde used as its operators. For 0 it produces 1, and for 1 it produces 0. And with these 3 operations we can manipulate every single bits within bytes forming the image pixels. For example, to set the nth bit in some byte to 1, it's enough to make the OR operation of that byte with a mask consisting of the nth bit equal to 1 and all the remaining bits equal to 0. To clear or reset or set to 0 the nth bit in some byte, it's enough to make the AND operation between that byte and the mask consisting of all ones and only one 0 at the nth position. And to test the current value of some bit, we need to make the AND operation between its byte and the mask having 1 at the nth position, and with all remaining bits reset to zeros. Okay, right now when we know how to perform the single bit operations, let's see how this steganography works. In steganography, we take advantage of the fact that with millions of colors that can be recorded using 4 bytes per pixel, the human eye is unable to distinguish them. The subtle differences are completely impossible for us to notice. You haven't seen any difference between the two images of the Braniński Palace in Białystok, have you? So, we can sacrifice 1 or 2 of the least significant bits from each byte to hide some message and leave the remaining 6 or 7 bits for the original image. In the simplest case, just to show the idea of steganography, we can use a message we can use as a message some other image which meets the following criteria. It has the same size, the X and Y dimensions, as the host image. It has much lower color depth than the host image, and the host image is saved in the lossless format, let's say in the PNG format. Okay, after presenting the idea, let's go to the point, to the code. First, let's see the function reading image data into the flat array of pixel color data bytes. On the left, we have the necessary imports and constants definitions, and the description of array we get as a result. At the index 0, this array will have image dimensions saved width and height. At the indices from 1 to width times height, we'll have the pixels bytes 3 or 4 per pixel, only RGB or with the alpha channel added. And on the right side, we can see the sample implementation of the image data reading function. This is a slightly modified example taken from the PNG.js library documentation. In the main part of this function, we iterate first over the rows of the image and then over the columns within the row. The first line of the inner for loop body converts two-dimensional coordinates within an image to the index of our flat array. And the double left angle brackets symbol denotes the shift left operator, which is equivalent to ×4 multiplication. Then we push all the color planes data, including the alpha channel, to our array. In this slide, we see simple implementations of both the encoder and decoder functions. The encode function takes as parameter two paths, the path to the host image and the path to the resulting encoded image, and the array with message to hide data. The encoding process works this way. We take the RGB color planes values from the message data array, compare them with some threshold value. On the previous slide, it was set to the half of the full byte range, that means to the 128. And depending on the result of the comparison, we set the least significant bit of corresponding color plane in the resulting image to 1 or clear it to 0. This is the place where I use the bit operations AND, OR, and masking selected bits. And at the end, after processing all pixels, we save the encoded data to the output file. In the decode function, the iterational part is very similar to the previous one. And in the body of the inner for loop, we read the least significant bits and of all color planes of each pixel from the encoded image. And according to the value of these least significant bits, we do some kind of upscaling. When the value is 0, we set the value of corresponding color plane in the decoded image to 0, and when the value red is 1, we set the corresponding decoded image color to all ones. It means 255. And at the end, we save the decoded image to file. And how long is the message we can encode this way? The Braninsky Palace photo presented earlier is 1500 per 300 pixels. This means it has 450,000 pixels in it. Taking the two least significant bits from each of the color planes, even excluding the alpha channel from each pixel, we have 6 bits per pixel available. And having a plain text set with the US ASCII character encoding, we can take only part of the character set, let's say 64 characters. It is enough to have all one-case letters, digits, and most of the punctuation marks. And 64 characters we can encode in 6 bits, so we can encode 1 character per pixel. Thus, in the Braninsky Palace image, we can encode 450,000 characters. It's quite a big book, isn't it? And we can say that the way itself, we encode characters in these 6 pixels, is one more level of cryptography. Okay, it was just one simple example of the steganography idea. In more general way, it can utilize not only images, but other media files too. And it's time to fulfill the promise made to show you the message hidden in the Braninsky Palace photo. It was, of course, I love WarsawJS image. Thank you for your attention.